So good morning, sir, and good morning all. And I am Karthik Ragul from IIT Chennai, pursuing BTech Computer Science and Engineering. And I am here to deliver my speech on Fermat's analysis theorem for my digital assignment 3 in the course Blockchain and Cryptocurrency Technologies. So first of all, what is Fermat theorem? Fermat little theorem, it is a kind of fundamental theorem in elementary number theory, which provide the computing powers for integers to modular prime numbers. So this theorem, it is a specific case of the Euler theorem, and it is an essential in application of elementary number theory, such as primality testing and public key cryptography. And this theorem states that if P is prime, then A multiplication of P is congruent to A mod P for all A. And an alternative form of this theorem also states that A power P minus 1 is congruent to 1 mod P, and where here A is an integer and P is a prime number, and A should not be divisible by P. So if this condition satisfies, then Fermat theorem for the given operation satisfies the problem. So this is the proof of Fermat theorem, in which Zp is the set of integer 0 to p minus 1, which when multiplied by a modulo p, the result includes all the element of Zp in some sequence. And moreover, a into 0 is congruent to 0 mod p. Therefore, the p minus 1 numbers are the only number which in the range 1 to p minus 1 is in same order. So the multiplication of the numbers in both steps, taking the result mod p, gives the following formula: a power p minus 1, which is congruent to 1 mod p. So let us take on the example in Fermat's theorem. And here we have given a prime number 5, p as 5 and a as 2. So we know 5 is prime number, and a is given integer 2. So when we put into this formula a power p minus 1 congruent to 1 mod p, we get 2 power 4 congruent to 1 mod p. Then we get 16 congruent to 1 mod p. So we know that 16 mod pi is resultant as 1. Therefore, for the given problem, the Fermat's theorem holds true for p equal to 5 and a equal to 2. So when we see at next example, we have given us p equal to 13 and a equal to 12. So when we put this into this formula, we get 11 power 12, which is congruent to 1 mod 13. So we know that 11 power 12 is somewhat huge number. Therefore, we know that 11 is 2 lesser than 13. So we put here as minus 2 power 12, which is congruent to 1 mod 13. Therefore, we can write 12 as minus 2 power 4 into 3, which is congruent to 1 mod 13. So we get the result as 3 power 3, which is congruent to 1 mod 13, and 27 mod 13. We know that it is 27 mod 13 is 1. Therefore, the Fermat theorem holds true for p equal to 13 and a equal to 11. So let us take this example. We have given p as 6 and a is equal to 2. So from this, we can easily conclude that p equal to 6, which is not a prime number. 6 is not a prime number. So we can conclude this does not satisfy the Fermat theorem. But anyway, if we put this into this formula, we get 2 power 5, which is congruent to 1 mod 6, and we get 32 mod 6, which is not equal to 1. Therefore, the Fermat theorem does not satisfy for this equation. So when we see the next example here, this is somewhat different compared to previous 3 examples. So we need to find the remainder when we divide 3 power 1 lakh divided by 53. So we know that 53 is a prime number. So we can apply a Fermat theorem. So 3 power 53 minus 1, which is congruent to 1 mod 53. And we know that we need to check 3 power 53, 52 is mod 53 is equal to 1. So to simplify this process, we have to raise both the sides to a larger power, so which is close to the value 1 lakh. So the quotient here is 1923, which can be found by dividing this value, and the remainder is multiplying both the sides with 1923. Therefore, when we raise 1923 to both the sides, we get 3 power 52 the whole power 1923, which is congruent to 1 power 1923 mod 53. Therefore, in the result, we get 3 power 99,906, which is congruent to mod 53. So, when we multiply both the sides with 3 power 4, and we get 3 power 1 lakh, which is congruent to 3 power 4 mod 53. So, in the result, we get the remainder as 28, which when you divide by 3 power 1 lakh divided by 53. So, to find the modular inverse by hand, we find somewhat difficult. So, I have done a Python implementation to find the modular inverse, so that we can simplify this process. So here in this program, m should be a prime number. So in this function GCD, I have given two values, and if b is double equal to 0, then we should return a, or else we should return the a mod b as b. And in the second function, I have given the power of x power y, and if y is equal to 0, then we should return 1, or else we should compute the value of p, which is the power of x comma y floor division. So why we have given floor division is that to round it off to the nearest number, mod m. Then we should return p if y mod 2 is equal to 0, or else we have to compute the modulo of x multiplication into p, the modulo of m. So in the final function, if the GCD of the integer a and m is not equal to 1, then we have to find the inverse doesn't exist, or else we have to find the multiplicative inverse, which is the power of a comma m minus 2 comma m. So here I have given two values, a equal to 3 and the prime number m equal to 11. So when we run this program, we get the multiplicative inverse as 4, which is true for the given values a equal to 3 and m equal to 11. So that's it when we look about Fermat's theorem. Next, we go to Euler's theorem. So first of all, what Euler's theorem is? It is a general generalization of Fermat's theorem, handling with the powers of integers modulo positive integers. So in Euler's theorem, it increases in applications of elementary number theory, such as the theoretical supporting structure for the RSA crypto system. So when we look at Euler's theorem here, for every positive integer a and n, so here there is no prime number. Both the integers a and n are positive integers, which are said to be relatively prime compared to each other. Then a psi of n is congruent to 1 mod n. So where here psi of n is the Euler's torsion function, which is very important in this Euler's theorem, because we have to first compute the value of Euler's torsion function, then only we can prove whether the Euler's theorem is satisfied for the given problem or not. So this Euler's torsion function counts the number of positive integers less than n, which are relatively prime to n. So when we look at the Euler's torsion function, it is also called as Euler's phi function. It can discover the number of integers which are both smaller than n and relatively prime to n. So this plays an essential role in cryptography. This set of numbers defined by z into n, which are smaller than n and also relatively prime to n. So in number theory, Euler's quotient function counts the positive integers up to a given integer n, which are relatively prime to n. So we can denote psi of n as the Euler's quotient function. So in Euler's quotient function, we can produce collisions in any of them with the current or foreseeable technology, so that the security you get here is identical. So for Euler's, before we satisfy the Euler's theorem, we have to compute the Euler's quotient function, and we have to check for three conditions here. First condition is we have to check if n is prime, or else we have to check if n is multiplication of p into q, where p and q both are prime numbers, or else we have to check n equal to a into b, where a or b, either of one is composite numbers. If any of one of these conditions is true, then we have to apply the respective formula here. So first, let us look at the first example. We have to find the Euler's quotient function of phi. So here n is phi, and we know that we can easily tell that phi is a prime number. So we have to apply this formula here. I have to apply this formula here. Psi of n equal to n minus 1, when the condition is n equal to prime. So therefore we get psi of phi equal to 4. So therefore we can conclude that there are 4 numbers that are lesser than 5 and relatively prime to 5 for the given problem psi of phi. Next, when we take psi of 35, we know that 35 is a product of 2 prime numbers, 5 into 7. So when we get this condition, we have to apply this formula, psi of n equal to p minus 1 into q minus 1. So when we apply this formula, we know that p equal to 5 and q equal to 7. So we get psi of 35 equal to 4 into 6, which is equal to 24. So we can conclude that there are 24 numbers that are lesser than 35, which are relatively prime to 35. So instead of applying Euler's quotient function, if we do it manually by computing the GCD of all the 35 numbers, then the time we take will be more. We know that if we compute the GCD of all the numbers, then also we get the result as 24. But if we apply Euler's quotient function, we can save more time. So when we look at this last example, psi of 1000, we know that n equal to 1000, which is equal to 2 power 3 into 5 power 3. So there are distinct prime factors, which are 2 and 5. So therefore we have to apply this formula, where n into 1 minus 1 by p1 into 1 minus 1 by p2, and so on, for the given number of p we have. So when we apply 2, when we put 2 and 5 into this formula, we get the result as 400. And this is another problem for 7000. We have 3 factors here. Instead of p1, p2, we also need to take a p3 value here. And if we compute the Euler's quotient function for 7000 here, comes to 2400. So after computing, after we know that we know how to compute Euler's quotient function, we can prove the Euler's theorem for given integers a and n. So here in this first example, we have a equal to 3 and n equal to 10. So for the given values, we need to apply the Euler's theorem here, which is a power psi of n is congruent to 1 mod n. So when we apply, when we put a and n values into this formula, we get 3 power psi of 10 is congruent to 1 mod 10. We know that psi of 10 equal to 4. So therefore 3 power 4 is congruent to 1 mod 10, and we know that 81 mod 10 is equal to 1. So therefore the Euler's theorem holds true for these values, a equal to 3 and n equal to 10. Then when we look at the second example, we have given us a equal to 2 and n equal to 10. So when we put these values into the Euler's theorem, we get 2 psi of 10, which is congruent to 1 mod 10. And we know that psi of 10 equal to 4. So we put 2 power 4 is congruent to 1 mod 10. But in the result, we know that 16 mod 10 is not equal to 1. So therefore, for the given values a equal to 2 and n equal to 10, the Euler's theorem does not hold true for these values. So when we look at the last example here, we are given as a equal to 10 and n equal to 11. So when we put this into the formula, 10 power psi of 11 is congruent to 1 mod 11. We know that psi power 11 equal to 10, as we have seen previous examples for Euler's quotient function. And 10 power 10 is congruent to 1 mod 11. So we know that 10 is 1 shorter than 11. So therefore we have put here as a minus 1 power 10. And we know that minus 1 power 10 is 1, and 1 mod 11 is equal to 1. So therefore the Euler's theorem holds true for this.